This video is going to review all of your inorganic nomenclature rules from Chem 1. Remember that there are two main types of compounds. We have molecular compounds and ionic compounds. Molecular compounds are going to contain two or more nonmetals, something like ammonia with nitrogen, hydrogen, or water with hydrogen, oxygen. While ionic compounds contain a metal and a nonmetal, like sodium chloride, for example. Looking at your periodic table, you'll note the bold stair step near aluminum. Anything to the left of the stair step is a metal. Anything to the right of the stair step is a nonmetal. Whenever we're dealing with molecular nomenclature, all of the nonmetals can combine in different amounts. For example, nitrogen-oxygen can form all of these different compounds whenever you have different numbers of the atoms all together. Your molecular nomenclature rules are that you're going to name each element, use prefixes to determine how many of that element you have. Remember your metric prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. The first element you're going to name as is, but you're going to change the ending of the second element to IDE. Let's go through a few examples. We have N2O5. N is nitrogen. Its subscript is 2, so it will have a prefix of di. O is oxygen, but change the ending to IDE, so that will be oxide. And it has a subscript of 5, so it gets the prefix of penta. Look at P4O10. P is phosphorus. The subscript of 4 is tetra. O is oxygen. So yeah, again, you change the ending to IDE, so it's oxide. And the prefix for 10 is deca. And note that you can drop the A whenever it's followed by oxide or something with another vowel. Some special situations that occur. The prefix is omitted if there's only one of the first element. So if the first element only has a subscript of 1, it will not have a prefix. It will not have mono on it. For example, CO2, C is carbon, and there's only one of them. So you simply list carbon, and it will not have a prefix. The O2, O is oxygen, so it becomes oxide, and the prefix for 2 is di, so it's carbon dioxide. The second element will always have a prefix. So mono is omitted on the first element, but not on the second. Look at N2O. N is nitrogen. The 2 is di, so it's going to be dinitrogen. And then the O is going to be oxide, and even though there's only one of them, it is the second element, so it needs a prefix. So this will be monoxide. Feel free to take a moment and pause the video to try these examples and resume when you're ready to check your answers. For SF6, S is sulfur, F is fluorine, so it becomes fluoride, and it will have the prefix of hexa for 6. So this is sulfur hexafluoride. For N2O3, N is nitrogen, 2 is going to be a prefix of di, O will be oxide, and the 3 will be a prefix of tri. So this will be dinitrogen trioxide. For PCl, there are no subscripts. So P is phosphorus. Remember, since this has a subscript of 1, it will not have a prefix. Cl is chlorine, so it becomes chloride, but it is the second element, so it needs a prefix even though there's only one. So this will be phosphorus monochloride. You can use the same rules when writing formulas from the name. So for oxygen difluoride, oxygen is O. There's no prefix, so there will be no subscript. Difluoride, fluoride is F, and di means 2. So this will be OF2. With dinitrogen triiodide, dinitrogen, nitrogen is N, di means that there is 2. Triiodide, be careful when you're reading this because some people go fast and they just see the O and put oxide instead of iodide. Iodide is I, and the tri is going to be a subscript of 3. So this will be N2I3. Let's review ionic nomenclature. An ionic compound forms when electrons are transferred and the resulting oppositely charged ions attract one another. So in the picture, if you notice, the pink sodium ions are sandwiched between the green chloride ions. Remember that atoms will become ions by gaining or losing electrons. So magnesium will become magnesium with a +2 charge. Remember that the number of protons stay the same, but the number of electrons change. So magnesium is going to have 12 protons and 12 electrons, but the magnesium ion with a +2 charge will still have 12 protons, but only 10 electrons, so it lost 2 electrons. With fluorine, so fluorine will become fluoride with a -1 charge. Fluorine has 9 protons and 9 electrons, but whenever it becomes an ion, it still has 9 protons, but it gained a negative electron to give it that negative charge, so it now has 10 electrons. Our representative elements will always obtain the same charge when they ionize. So our group 1 metals will have a positive charge, including hydrogen when it is acting as the positive ion. Our group 2 metals will have a +2 charge. Our group 3 metals, like aluminum, will have a +3 charge. We tend to not have ions in group 4. Group 5 starts our nonmetals. So remember, for nonmetal charges, it is the group number -8. So where nitrogen is in group 5, we'll have a -3 charge. Our group 6 nonmetals, where oxygen is, will have a charge of -2. Our halogens, that group 7 nonmetals, will have a charge of -1. And noble gases do not have a charge, and they do not form ionic bonds. Whenever we're writing ionic formulas, we have to make sure to balance the charges. Compounds overall have a charge of 0. So we want to account for that. So let's look at whenever we are combining elements like sodium and sulfur. Sodium is in group 1, so it has a +1 charge. Sulfur is in group 6 with a -2 charge. If we combine these with 1 atom of each, the overall charge is going to be -1. So this is an incorrect ionic formula. The better way to do this, looking at sodium and sulfur, is we tend to crisscross charges to balance them. So we need 2 of the positive ions to equal 1 of the negative sulfur ions. That would give us a formula of Na2S, which has an overall charge of 0 and is balanced and neutral. Whenever we're writing formulas, you want to write the cation first with its charge and the anion second with its charge. You balance the charges so the compound is electrically neutral. Make sure that they cancel out. And the formula will not contain charges at the very end. It will only have the symbols and the subscripts. And the subscript should be in the lowest possible ratio. So if it's a +2 and a -2, you're not going to have 2 subscripts that are 2. You would reduce those to be 1 and 1. Let's look at some practice examples. We have magnesium chloride. Magnesium is Mg with a positive 2 charge. Chloride is Cl with a negative 1 charge. Whenever you balance these or crisscross these, you get MgCl2. For aluminum oxide, aluminum is Al with a plus 3 charge. Oxide is negative O with a negative 2 charge. Whenever you crisscross those to balance them, you get Al2O3. For sodium iodide, sodium is Na with a positive charge. Iodide is I with a negative charge, so that will make NaI. For calcium oxide, calcium is Ca with a positive 2 charge. Oxide is O with a negative 2 charge. Whenever you crisscross these, you would get Ca2O2. But remember, the subscripts have to be in the lowest possible ratio. So we would reduce that to CaO. For potassium sulfide, potassium is K with a positive charge. Sulfide is S with a negative 2 charge. When you crisscross that, you get K2S. For lithium fluoride, lithium is Li with a positive charge. Fluoride is F with a negative charge. Whenever you crisscross them, you get LiF. Whenever you're naming an ionic compound, so you have the formula and writing the name, you want to name the cation first, and then name the anion by changing the ending to IDE. And this is only in binary ionic compounds. These are going to be things right off the periodic table. So this will be a monatomic ion from the periodic table, not something like peroxide, which is O2. Even though oxygen is on the periodic table, it already has that subscript. We are not going to use prefixes when naming ionic compounds. We're going to take a couple minutes to do some examples. So for BeO, Be is beryllium. All the cations you name as is and do not change them. O is oxygen, so in a compound it will be oxide. For MgBr2, Mg is magnesium, Br is bromine, so in a compound that will be bromide. Take a moment to pause the video and try the next two and come back when you're ready for your solutions. For K2S, K is potassium, S is sulfur, so it becomes sulfide. So this is potassium sulfide. For Li3P, Li is lithium, P is phosphorus, so in a compound it will be phosphide. That was with representative metals. We have to do something different whenever we have transition metals. Whenever there are transition metals, so those group B elements in the middle, the charge cannot be determined based on the periodic table position. Remember, transition metals can lose different amounts of electrons and have multiple possible charges. Your exceptions that only have one possible charge, make sure that you know these always. You have silver Ag with a positive 1 charge, cadmium Cd with a positive 2 charge, and zinc Zn also with a positive 2 charge. So there are two different methods to giving the transition metal charge. There's the stock system, which is the common system that we use, where the charge of the metal is given as a Roman numeral after the name of the metal. And then there's the classical system, which uses suffix on the metal name, often derived from the Latin name. Whenever you see the classical system, it'll either have an ending of us or ic. Whenever it ends in us, the OUS, that's the lower of the possible two charges. If it ends in ic, that's the higher of the possible two charges. Let's look at some examples. Here we have lead and copper that are both written in the stock system. Note the Roman numerals after the metal indicating the charge of the metal. So we have lead 2 chloride, meaning that we have lead Pb with a positive 2 charge. Chloride is Cl with a negative 1 charge. And then you crisscross like you would with any other ionic compound. So this would be PbCl2. For copper 1 sulfide, copper is Cu. Here it has a positive 1 charge, indicated by the Roman numeral. And sulfide is S with a negative 2 charge. Crisscross your charges to balance, and we have Cu2S. Ferric oxide is written in the classical system. So noting the ic suffix means that this is the higher of the two charges, and Fer, the Fe, is iron. So remember, looking at your common transition metal charges on your memorization sheet, iron can either be a +2 charge or a +3 charge. The ic indicates that it is the higher, the +3 charge. So this will be iron, Fe, with a +3 charge, and oxide is O with a -2 charge. Crisscross your charges and you get Fe2O3. Naming works the same way. You are going to name the cation and the anion, but you have to remember that it does need Roman numerals in order to determine the charge. So for NiBr2, you're almost going to uncrisscross them to figure out what the Roman numeral should be. So that is going to be made from nickel with a +2 charge and bromine with a -1 charge. So that is nickel 2 bromide. For Cr2O3, if you uncrisscross the subscripts, you get that it's chromium with a +3 charge and oxygen with the -2 charge. So this is chromium 3 oxide. This works 90% of the time. Now look at PbO2. Whenever you uncrisscross this, you have lead with a +2 charge and oxygen with a -1 charge. Now from what you know, oxygen has a charge of -2. That indicates that this has been reduced. So the actual charges are lead with a +4 charge and oxygen with the -2 charge that's normal for it. So this is lead 4 oxide. Be careful of that whenever you are uncrisscrossing to figure out the charges. Pay attention to if it has been reduced or not. Another aspect to ionic naming is whenever we have polyatomic ions. These were on the back of your Chem 1 reference sheet, but we don't have that on our reference sheet. You have to refer to your memorization list and study these. Polyatomic ions are a group of 2 or more atoms that are chemically bound together and act as one ion. So whenever they are bonded together, they have an overall charge that can bond ionically. An example of this is sulfate. Sulfate is SO4 with a -2 charge. That is a substance that is covalently bound together, sharing electrons, and whenever it shares electrons, they have an overall -2 charge. This is always going to stay together. So if we were writing the formula for a compound between potassium and sulfate, potassium is K with a +1 charge. Sulfate is the SO4 with a -2 charge. You still crisscross your charges as necessary. So this would be K2SO4. Even though we have a subscript of 2 and 4, that 4 is part of sulfate. So you're never going to reduce that. For polyatomic ions, all the polyatomic ions except for one are negative ions. Your exception is ammonium, which is your NH4+. All but 2 of the negative ions end in ITE or ATE. So that's what you're going to see the most, indicating that they have oxygens in them. Your 2 exceptions you need to know are hydroxide, OH negative, and cyanide, which is Cn negative. We're going to write the formulas using the same ionic compound rules. So we're still going to write our cation and our anion, crisscross our charges, and reduce as needed, remembering that you are never going to reduce the actual polyatomic ion. So here's some examples. We have sodium nitride, so that IDE ending often indicates it's a monatomic ion off the periodic table. So we have sodium nitride, which is Na plus with N negative 3 for nitrogen. Crisscross your charges and you get Na3N. Sodium nitrite, sodium yet again is Na plus. Nitrite is NO2 with a negative charge. Crisscross your charges, you get NaNO2. Sodium nitrate means that there's more oxygen in this one. So it's sodium Na plus and nitrate NO3 negative. Crisscross your charges and you get NaNO3. And remember, do not change the subscripts of polyatomic ions. They have to stay the same. And you should put the polyatomic ion in parentheses if there should be more than one of them. So say that your cation has a charge of 2 and your anion has a charge of 1 and is a polyatomic ion. You don't want it to look like you have 2 of that last element. You want to indicate that there are 2 of the entire polyatomic, so you put it in parentheses with the subscript on the outside. Let's look at some examples. We have lithium phosphate. Lithium is Li with a positive charge. Phosphate is PO4 with a negative 3 charge. When you crisscross charges, it's Li3PO4. For aluminum nitrate, aluminum is Al with a positive 3 charge. Nitrate is NO3 with a negative charge. Whenever you crisscross, you don't want it to look like there are 33 oxygens, so you need to put the nitrate in parentheses. So this will be AlNO3, 3. For magnesium hydroxide, magnesium is Mg with a positive 2 charge. Hydroxide is OH with a negative 1 charge. Remember, crisscross your charges, and you want it to look like you have 2 hydroxides, not 2 hydrogens, so don't forget your parentheses to make MgOH2. For calcium carbonate, calcium is Ca with a positive 2 charge. Carbonate is CO3 with a negative 2 charge. When you crisscross these, the 2 charges are going to cancel out, so there will be no subscripts. So this will be CaCO3. And then ammonium, remember our only positive polyatomic is NH4 plus. Chloride is Cl negative. Whenever you crisscross these, you end up with NH4Cl. All ionic naming rules apply, but you do not change the ending. So you are never going to change the ending of a polyatomic to IDE. Leave it as is on your memorization list. Let's go through some of these. We have KClO3. Remember, K is potassium. ClO3 is chlorate. So this is potassium chlorate. Na is sodium. OH is hydroxide. Al is aluminum. SO4 is sulfate. CuNO3, 2. Cu is copper. Remember, copper is a transition metal, so you need to include Roman numerals. NO3 is nitrate. When you uncrisscross these, you discover that it's copper 2 nitrate. Then we have FeOH3. Fe is iron, and it is a transition metal, so you need your Roman numeral. And OH is hydroxide. When you uncrisscross this, you figure out it's iron 3 hydroxide. We also have special rules for naming acids. acid names are based on the normal ending of the anion. So does it end in IDE, ITE, or ATE? If our anion ends with IDE, it's going to have the prefix of hydro and end in ic acid. So look at HBr. Br in a compound is going to be bromide. So we are going to change this to be hydrobromic acid. If the anion ends in ATE, it's not going to have a prefix, but it will end in ic acid. So look at HNO3. NO3 is nitrate, so this will become nitric acid. And anions that are ending in ITE are going to become acids that end in us acid. So look at H2SO3. SO3 is sulfite, so this will become sulfurous acid. We also have compounds that are considered hydrates. These are solid compounds that do contain water molecules. So the ionic compound is bonded to water molecules. You'll notice that it has the ionic compound written. There will be a dot in the middle indicating its attachment to water molecules. Whenever we're naming these, you want to name the ionic compound first, and then use the molecular prefix to describe the number of water molecules attached or hydrates attached. So our example listed is CuSO4.5H2O. So you want to name the CuSO4 first. Cu is copper. It is a transition metal, so it does need Roman numerals. SO4 is sulfate. Sulfate has a -2 charge, so copper here must have a +2 charge. So this will be copper 2 sulfate. And then the 5H2O, the prefix for 5 is penta, so this will be pentahydrate.